Hello and welcome to the presentation of LSTM and convolutional autoencoder based abnormality detection for heterogeneous autonomous systems. We're team BUET Andromeda. We will start with the problem definition. The goal of our problem is to detect abnormalities in the behavior of ground and aerial systems based on embedded sensor data in real time. Now we break that down in simple terms. While detecting abnormalities, we are interested in ground and aerial autonomous systems such as self-supervised cars, drones, etc. In a perimeter monitoring system where the agent is the drone, it might face a sudden abnormal jerk or it could be flipped mid-air. We want to be able to identify abnormal situations such as these. Our autonomous system relies on embedded sensors such as IMU sensor and digital camera to collect data, which together represent both the condition of the system and its surroundings. We also need to provide an inference of abnormality in real time before new data arrives in the following time step. Now let's discuss the challenges we face while finding the solution to this problem. First, we are working with unlabeled data, so we had to reformulate the task as an unsupervised learning problem. We also need to follow a multimodal approach to process the multisensory output in the form of sensor as well as image data. For video feed, we are more interested in the motion state of the system over the semantic content of the image, prioritizing self-abnormality over environmental abnormality. Instead of binary classification, we needed to provide a continuous score between 0 and 1, 1 being the highest abnormal. We also needed to identify and explain the sources behind the abnormality in a given situation. And our models must be fast responsive to give inference in real time. To overcome these challenges, we streamlined our problem to 3 solution approaches. First, we used traditional machine learning methods of one-class classification such as one-class SVM and isolation forest on the raw data. Second, we used hybrid networks where we trained a deep neural network and extracted features from it for our one-class classification algorithms. And finally, we trained an end-to-end deep neural net and used a scoring function along with it to give abnormality predictions. Of all the approaches, the end-to-end network performed the best, and that's what we use in our framework. We will now provide a complete overview of our framework. We use 2 different models for 2 different modes of data. The first of which gives abnormality predictions on sensor data and is shown here. The IMU sensor data is pre-processed and turned into sequences made up of data from 5 timestamps. It is then sent to an encoder-decoder LSTM that tries to reconstruct the same sequence. We get some reconstruction loss for each feature in every timestamp for that sequence. Then we average the loss over all 5 timestamps and send it to our scoring function. That gives us scores representing abnormality contribution by every feature. We average that and finally get an abnormality score in probabilistic sense on the timestamp in the middle. Our model can also pinpoint the source behind the abnormality. From our scoring function, we get abnormality score for all the features. Then we get category-wise abnormality by averaging related features of the category. Our second model shown here gives predictions on the video feed. The images are pre-processed and optical flow is calculated between successive images. The flow vectors are then sent to a convolutional autoencoder that tries to reconstruct them. Similar procedure is followed hereafter. We get some reconstruction loss for the optical flow vectors, which we send to our scoring function, and that gives us the final abnormality score on the timestamp. Let's discuss the models in detail now. First, we will look at our encoder-decoder LSTM model operating on sensor data. But before that, we need to talk about sensor data preprocessing. We use 10 features on each timestamp to train our model. First, we have orientation in the X, Y, Z, and W directions, linear acceleration in the X, Y, and Z direction, and finally angular velocity in the X, Y, and Z direction. These data are then normalized according to their respective topics and merged to produce a feature vector of size 10 for that particular timestamp. Then we append that feature vector to the end of 4 previous feature vectors obtained from the 4 previous timestamps. This way we build sequences of size 5 by 10 with an 80% overlap between successive sequences, which we then feed into our model. Now we move on to our encoder-decoder LSTM model architecture. First, our sensor data is fed into the encoder LSTM in the form of a sequence. The data is then processed sequentially through the encoder LSTM network, and we only use the output after the final timestamp, which is our reduced domain representation. This is then repeated 5 times before sending it to the decoder LSTM for ensuring size compatibility. The decoder LSTM takes this sequence as input and outputs another sequence. The output sequence is essentially made up of all outputs from all previous timestamps. We then pass these outputs at each timestamp to a dense layer, which basically decompresses the outputs to the same shape as the original input, consisting of 10 features per timestamp. During training, our model tries to produce an output as close to the original input as possible and minimizes reconstruction loss. Since it was trained on normal data only, it produces low reconstruction loss for normal data and high reconstruction loss for abnormal data during inference. We use this property to give abnormality scores later.
The unique challenge for our image model is to identify system motion from image frames, which is different from understanding the semantic content of an image. To address this, we use optical flow instead of directly operating on RGB images. Optical flow can efficiently encode the motion between 2 subsequent image frames. First, we demonstrate the optical flow for a normal condition. If we look closely, we see that there is a clear structure in the flow of normal images. Next, for the abnormal situation, we see the flow vectors are very noisy and occluded. These visualizations demonstrate the remarkable effectiveness of flow features for abnormality detection. We use dual TVL1 as a flow estimation algorithm. Compared to other methods, TVL1 is both fast and robust. We also use a GPU implementation of the method that gives us about 4 times speed up in flow estimation time. Next, we describe our convolutional autoencoder model to process the optical flow features. For a pair of images, our dense flow method returns a two-channel matrix, the first channel representing the horizontal motion of each pixel and the second channel for vertical motion. The encoder of the network uses a series of 3x3 convolution and downsampling layers to compress the input by a factor of 256. This bottleneck forces the network to learn a good representation of the normal flow vectors. The decoder of the network is symmetric to the encoder and also uses a series of 3x3 convolution and upsampling to reconstruct the input. Since the network is trained using only normal flow maps, the reconstruction loss for abnormal flow frames will be very high. For downsampling and upsampling operation in our convolutional autoencoder, common choices are to use max pooling and transposed convolution, but these methods ignore the Nyquist sampling criteria and make our network highly stochastic. The figure here shows the reconstruction loss is very different for 3 different training trials. So we propose a signal processing fix. For any intermediate feature map, we first anti-alias it with a low-pass filter and then we sample it. Similarly, for upsampling, we use bilinear interpolation. We inflate the low-resolution feature map with zeros and then use a bilinear filter to fill in those values. Introducing these two anti-aliasing properties make our network much more stable across training trials.
Now we will describe how both our models work in conjunction with our scoring function to output an abnormality score. After training, we use our model to reconstruct the same data it was trained on. Naturally, the losses for each feature are concentrated around 0 with steady decline in frequency for higher loss. We approximate the frequency of losses as Gaussians and extract parameters mu and sigma from them. At inference, we send these mu and sigma along with the reconstruction loss for test data, and our scoring function uses these equations to give a final score between 0 and 1.
Now we will demonstrate the performance of our method. First of all, let us see the demonstration of real-time abnormality detection from sensor data. As we can see, the model perfectly detects normal and abnormal portions. Now let us see for images. When the system flips or shakes, the abnormality score is high. When the system is stable, the abnormality score is low. Now let us see how category-wise abnormality detection works. The black dashed regions indicate no sign of abnormality. The purple dashed regions indicate abnormality due to orientation and accelerometer. The two sources are found intercorrelated. The green dashed regions indicate abnormality due to high angular velocity. Here is a summary of the results. For normal dataset, box whisker plot is confined near 0 region, indicating no abnormality. For abnormal dataset, we can see a white plot as this dataset contains abnormality of different levels varying with time. The most time-consuming process in our solution is to calculate optical flow. We have boosted the speed of this process using GPU. For normal data, time required to calculate optical flow using GPU is 2 to 3 times less than that of CPU. Similar case is found for abnormal data. However, either CPU or GPU, time required for abnormal data is always higher. Now we can highlight on the importance of our proposed solution. We have proposed autoencoder based method for real-time abnormal detection from multimodal signal. Where traditional approach is to use threshold value to get abnormality from reconstruction loss, we have introduced a scoring function to get continuous score. The source of abnormality can also be detected from our method. The strength of our method is that cross validation was performed using data of totally different environment and the result was satisfactory and invariant of training data. As the nature of the model was different for sensor and images, we have kept the two models separate. We have improved our image model after the first phase of the competition. Anti-aliasing layer has been introduced with the autoencoder, which resulted in more stable training over images. We have speeded up the calculation of optical flow using GPU. Finally, we may indicate the direction of our future work. The time difference of optical flow calculation for normal versus abnormal indicates that the abnormality can be detected within optical flow calculation process itself, returning unnecessary steps and time. This may result in faster detection using low-power CPU. Though our sensor model was trained and tested using IMU data, if similar data of other sensors are available, we can test our sensor model on those. So that's it. We BUET Andromeda would like to thank you for your time.